Welcome to this virtual presentation of one of my two ICSOBA 2022 paper. This one is on the retrofit of several cell technology using Protruding collector bar cathode assembly. The initial title also involved that using cast iron rodding and preheating of the cathode block before the rodding. The main author is Liu Wei from SAMI, and you have a list of co-author from SAMI, and me, I was involved mostly by rewriting the text and preparing the presentation, and also doing some of the MHD modeling work. Okay, so I'm Dr. Marc Dupuis. I have a PhD in chemical engineering from 1994 from Laval University. I worked 10 years for Alcan International, and after that I created my own company, Venison Inc., that I'm operating since 1994. And I'm a consultant, mostly involved in the mathematical model of Hollywood cell. I'm consulting for SAMI, that's why I'm involved in this paper. So I will introduce the subject, and then after that I will present some modeling work, thermoelectric, MHD, and thermomechanical. Then I will present the concept of the cathode assembly. I will talk a bit about the cast iron rodding procedure that is new for China, because up to now they were using mixed rodding for their design. And I will present, I was able to obtain some KPI for their retrofit. I will present them. So the introduction is that SAMI has developed this, what they call new conceptual cathode technology. So MCCT is the name that they are quoting in papers. They have started to develop that in 2010. So they have implemented this in several smelters. So I will present the result of them. And they already presented the name MCCT was presented in a few papers, presenting the work they are doing for Inalum in Indonesia. But up to now, they never describe what it is with it. So I was able to convince them to present actually what it is. So that's what I'm going to do. So it was used in several smelters in China and in 2 smelters outside of China so far, in Turkey and Indonesia. So I'm starting with the modeling work. So they have they got from me a long time ago, 2005, training to use ANSYS to develop thermoelectric modeling based on ANSYS. So that's a typical model that they have used for studying the impact of changing the size of the bar on the horizontal current and the metal path. So that's before the implementation of this new concept and after, with a reduction of 40% of the horizontal current in the metal path. Then I will present a study that was done with image values to study the cell stability. So the model that was studied is a model of the SY500, so the SAMI technology at 500 kelvins. So that's the horizontal current that you get before the introduction of this new concept. That's so the horizontal current here and metal flow and the metal deformation, and then the actual stability study. So what was performed is here 4 ACD was modeled. The thickness of the metal pile is 18 centimeters. That will be important for the next set of results. So here you can see that when you go from 30 6 to 35, the cell is predicted to become unstable. So that's the first result. After that, after the introduction of the new concepts of the NCCT with the bigger bar and cast iron rolling, you obtain a much reduced horizontal current in the metal pad. You obtain more or less the same flow, but a bit less intensity, and more or less the same but metal deformation. Again, a little less total deformation. And what is critical as a result is here now we are predicting that the cell will be stable at 26 millimeter ECD with up to 19 centimeter metal pad. So here, contrary to the first study, it's the thickness of the metal pad that is changing from 24 going down to 17. And the last two, 18 and 17, your prediction of an unstable cell. The term C that is quoted here is referred to a new feature in MHD Valdez code. We have presented a previous paper where we are discussed the need for this implementation of this new term or new feature in MHD Valdez when we are studying very low ACD, like 26 millimeter. And if you don't use this new parameters, you don't survive the initial transient here, because the burn off of the anode is not complete, and you have a short circuit at the very early here. That is not an indication of a stable or unstable cell. It's just that the anode is not adjusted to the flat metal deformation quickly enough to survive this first period of simulation. So it's an internal detail. It's not that important for the user, but it's very critical. Of course, if you don't survive this initial time, you don't know if you don't have a result if it's stable or not stable. You have to survive this initial time, and the need for this new parameter. Okay, so this is the MHD part. After that, there's a thermoelectrical, thermomechanical modeling of the cast iron process, the preheating, and then the so the gas preheating was studied. Here they compare preheating up to 400 degree and preheating up to 500 degree. It's not that different, but they decided to go with 500 degree. I don't have enough detail to be very good about explaining what the total work here. I'm presenting those two results here, and more importantly, here they're comparing the influence of the radius in the corner of this radius here in the corner of the slot. If it was already presented in previous paper that it's an important parameter, and then this modeling work confirmed that it is important to change the radius here to prevent have some cracking to exceed the crack the limitation for the obtaining a crack here. Okay, so now this finally I can show what is NCCT. So it is so those bars they are protruding, so they are much higher than the slit. The bar is much higher than the slit. So a big part of it is outside of the block. And that's a way to have a more conductive bar. And they have patented this, but I discovered that there's a patent, much older patent that was on the same concept that exists. In the Chinese patent, there you see this figure. So the part of the concept is to also put some castable around the protruding part, so it's easier to build the lining when it's time to put the block in the pot, the block in the pot. Okay, so this is the concept. In the paper, there's some discussion about the ratio about some of those values here. We'll say it's important, and the wing span is important. Of course, if it's too small, we have some cracks that can form. And there's also a discussion about this ratio between those two numbers. Okay, so after that, it's a preheating. So before up to now in China, they were not using cast iron rodding for the block to collect the bar. So they never had to address this issue about how to preheat the block to prevent cracking. So SAMI has developed this device that is a preheating device that the crane puts on top of the block you want to preheat. And this device contains a lot of burner, and you control the burning rate to get the uniform preheating along the way. So they are very, in the paper there's a bit of discussion about this panel and not so much, but anyway, it's part of the concept to have developed this preheating system that is coming with the technology. The NCCT technology include this device. Okay, and then after that, they have done some tests about how to pour the cast iron in the block. So they have tested two approach. Either you put the cast iron in the outside bar, so 1, 2, and then go back to the other block 4, 5 here, and then you come back to the internal bar. So, or you do 1, 2, 3, 4. So you do the 2 bar for this side, 2 bar this side, and then you go around and you do, and they have discovered that it's not making much of a difference. So they picked the second sequence because it's simpler. And you have a picture where they are using this sequence. So it's a manual casting. So yeah, the guy had to move around with his crucible and adjust it. So it's simpler for him to do this block first and the second block second. It's not affecting the cracking that would have been, of course, if it would have been very different, they will have picked this one. If that being the case, that this is safer. Okay, so that are also discussed in the paper. You can see again the preheating device here. So they move this on top of the block. They preheat up to 500 degrees. They remove and then they pour the cast iron. And so once it's done, you have this. They look like this. So now you have the cast iron, but they are protruding. So it's not very convenient to put that block in the pot. So before doing that, there's an extra step where you put this castable. So there's a mold that you put around the block, and then you pour this castable. And when you're done, then you have this, the block look like this. And this, then the block will be put as a normal block would be put in the pot for the lining. And here we have a picture of one of the pot where it was implemented. So it's a pot room of the most recent pot room construction of SY 500 that now came standard with this new block design, block assembly. So this one was constructed directly with this technology, but many other were retrofitted. So I will go and start to present those. So this technology, the NCCT, was implemented in several pots in China, from 200 kilograms up to 660, they say here, but they don't operate at 660. The SY, they call it SY 600 now, and we will see that they are operating it now at 640 kilograms. So they have retrofitted several smelter in China and 2 outside of China, in Turkey and Indonesia. In Indonesia, they are in the process of retrofitting a pot line. But so far they have done only 3 pot that were done as a test pot. So this NCCT reduces in general the cathode voltage drop by 50 to 70 millivolt when you keep the same cathode grade. And you can get to 130 millivolt if you at the same time change the grade of cathode from semi-graphitic to graphite. So that's the list of all the smelter, the technology, the number of pot that was reported in this for the KPI, the grade of cathode, the millivolt saving here of the cathode voltage drop, and the date of implementation. So it goes from the oldest 2015 is the oldest, right? And the most recent 2020. Okay, and so the goes from 200 and up to 640 the average. The name changed from SY660 to SY600, and the amperage, current amperage that is reported here is 640. They have retrofitted mostly SAMI, so SY is for SAMI technology, so GP is for GAMI, so they have retrofitted this, but that is from GAMI's institute, this technology. Okay, and now I'm reporting the KPI obtained. So they are, except for the SY600, they are not too happy about the results, so they don't want to. I don't have the KPI for that last month. And the number you have to number reported here normally for acceptance test. So there's after implementation, there's a very short period of time where they're doing this calculation. So they are very good number because they are obtaining. It's not like the average operation after a long period of time. It is mostly concentrated to get those kind of excellent number. Well, excellent number for the energy consumption. Typically, in China, the current efficiency is not so good. You can go down as low as 90%. But if you look at the two energy outside of China, smelter outside of China, the Turkey and Inalum in Indonesia, you have very good current efficiency that are reported here for the same type of technology. So it's a kind of an indication that it's depend on how you operate those plant and what the quality of the anode you are using and several other things. So it's not necessarily that it would be impossible to do better for the current efficiency. Okay, so the conclusion or the summary of this those KPI that the average current efficiency of all those retrofit is 93.7 and the energy consumption 12.6 kilowatt-hour per kilogram. If you concentrate on the 3 smelter using the SY500, you get better current efficiency, 94.3, and better energy consumption a bit, 12.5. And here I was able to obtain a result before the implementation of the NCCT technology. So they moved from 92 to 94.3 and from 12.8 to 12.5. So in general, we have an improvement of 0.3 kilowatt-hour per kilogram by introducing this technology, this NCCT technology to your pot. So that's more or less the summary that this has been done in plenty of smelter. in China with success. Up to now, 2,600 cells have been converted from a range of operation from 200 kilograms to 640 kilograms. Reporting good KPI, except they don't report the 640 kilograms. So that summarizes this paper. Thank you very much for your attention.